In this tutorial, we're going to implement hybrid air-liquid systems as well as a direct liquid cooling system. I'll show you how to do it by modifying an existing system layout. First, I downloaded the zip file containing the executable and the associated support files from Dropbox. Then when you extract it, you get this distrib folder here. If we double-click on the distrib folder, you can see we have a number of input decks. We have the VTAS executable, we have the manual, then you have some support files up here listed in these directories. So what we'll do is we'll first run the command window. We'll go to the desktop and the distrib folder. If you do a directory listing, you can see that all the same files are in here. So we'll first run VTAS. You have to give it a minute so the GUI will pop up. And here, we'll first open input1.txt. This is the file we're going to modify. Click on Open and Run. It takes us to the end to where we just do the input checks. You can bypass a lot of the screens. You click on Next. This is the layout that we're going to run with it. And I'm going to click on Continue. Then we'll go. So this is the steady state solution for input1.txt. So you can see we have the data center that connects with one CRA. The CRA connects with the chiller with the cooling tower, and the cooling tower with the external air and water. The thing that we're going to modify here is this chilled water loop, the loop between the chiller and the CRA. So I'll show you how this can be done with a hybrid liquid air and direct liquid cooling system. We'll first look at the output from our input1.txt run. So the output is listed here in the output.txt file. So if we open this up, we'll save this then as output traditional. We'll minimize that. So as stated before, what we're going to do is modify the chilled water loop. We still have the CRA, we still have the chiller. Here we're going to integrate a hybrid air-liquid component in the form of a rear door heat exchanger. In order to do this, we're going to put in two junctions, a J1 and a J2. The chiller is going to provide chilled water to the first junction, which will then split it between the CRA and the rear door heat exchanger. As the water warms up in the CRA and the rear door heat exchanger, it's going to return then to J2, where it combines and goes back to the chiller. This is the plan we're going to implement now in VTAS. So returning to our screen here, we'll run VTAS again. Again, we'll open up input1.txt. We'll go through the first couple screens here and keep all the default values. One thing I want to show you is that if you look at fan F4, when we edit it, notice it's a fixed flow rate fan, and the fixed flow is 0.001 cubic meters per second. So this is the pumps that we're using in the liquid loop. So we're going to put in this fan F4 into our system. Now once we get to the rear door heat exchanger screen, we notice we don't have any, so we're going to add one by just typing in this box here and clicking on Add New. Now you get to specify the fraction of the rack heat output that's absorbed by the rear door heat exchanger, and we'll just leave the default as 0.7. Notice now we have it popping up here in the pull-down menu. But you can easily implement the same type of creation of in-row heat exchangers, overhead heat exchangers, and direct liquid heat exchangers. So in the data center itself, we're going to edit the first row, and you notice that we can apply then either the rear door, in-row, overhead, or direct liquid heat exchangers. If you click on the pull-down menu for rear door, notice that our RDHX1 pops up. We'll click on Next, then Next, and now it's been implemented in the data center. As we cycle through the external equipment, we have to add in junctions. So add in junction 1, and junction 2. Now we get to the loops. We have our 5 loops. The one that represents the chilled water loop is this LCH1, so we're going to edit that. The existing chilled water loop has two branches, one from the chiller CH1 to the cross C1, and one back from the cross C1 to the chiller CH1. We're going to delete both of those. So now we see we have none. So we're going to add our first branch. That goes from the chiller out to the first junction. We need to apply our pump, so we'll put down F4. You can see now it shows up as an existing branch. Our second branch goes from J1 to the CRA. The third branch is from J1 to our rear door heat exchanger. And notice that our rear door heat exchanger now is called RDHX-1. This is a subtle thing that's inherent to VTAS. When we define the rear door heat exchanger RDHX1, that is the type of rear door heat exchanger that we've defined. It isn't the actual one that we've implemented in the system. What we did in the data center block is we said that the first row implemented a rear door heat exchanger of type RDHX1. So this allows you to have multiple rear door heat exchangers of the same type in the data center without having to define each of them individually. What VTAS does by default is it'll name the placed rear door heat exchanger with the dash in it. So here, our placed rear door heat exchanger is RDHX-1. So we're connecting then the chilled water loop up to this placed rear door heat exchanger inside the system. Now if you look at our branches, we have all the supply branches in. Now we need our return branches. First, we can take it from the CRA to junction J2. Our second one is from the rear door heat exchanger to also the junction J2. And finally from junction J2 to the chiller. With all our branches, it looks like everything is set up right. If we click on Next, you can see that it does an input check for us, and sure enough, everything looks okay. So this is our new system here. You can see now, before we had just the two lines between the chiller and the CRA. Now we've got something a little more elaborate here. The chiller provides flow with a pump to the first junction. That junction then splits the flow to the CRA and the rear door heat exchanger, which then recombine at the junction, goes back to the chiller. So if we run this, and then get our output screen, and sure enough, you can see that there's heat exchange that can be calculated. The maximum heat exchange occurs in the cooling tower in our case here, and then the exergy destruction, the maximum amount occurs in the chiller. If we go back to our distrib folder, now we have outp, which is the output file from our modified input deck. And we can compare outp to our first one, outp traditional. If you look down to the steady state simulation results, you can see that adding this hybrid air liquid cooler had a couple of effects here. First, it had the effect of raising the POE and the WUE. And then also, it had the effect of reducing the CRA exergy destruction. So in the traditional system, it was 21.7 watts, and here it's been reduced to 18.5 watts. If you go to the bottom of this, you can see that the rear door heat exchanger provides an exergy destruction of 14.9 watts. So there is a net increase in the total exergy destruction of 5,204 versus 4,074. So in this particular case, adding the rear door heat exchanger actually was detrimental to the exergy destruction in the system. If you look further down here in the modified file, you can see that the rear door heat exchanger has been implemented both in the branches, as you can see here. They provide the flow rate and the temperature. Here is the inlet branch and the outlet branch. You see that there is a slight increase in the temperature of the water. And then at the bottom, it provides some information regarding the design characteristics of the rear door heat exchanger. So next, we're going to implement a direct liquid heat exchange system. It's very similar to what we did with the hybrid air liquid heat exchange system with a couple of small differences. So we'll first run VTAS again. And we'll open up our existing file, input 1, which we'll modify. So we go to the first couple screens here. Now the first difference between the standard hybrid air liquid system and a direct liquid heat exchange system is the fact that the direct liquid heat exchange system requires its own independent pump. So we're going to add in our new pump, FCDU. The This will be a fixed flow rate pump, and we have to provide it with the flow rate. I'll give it 0.0005, which is half of what the flow rate that's entering the chiller is. And we have the efficiency of 0.8. So now, if you look here, we have our FCDO listed and our other fans and pumps. We'll go to our direct liquid heat exchange systems, and we'll add our first one in here, called LHX1, which we'll add, and the new screen pops up here for all the properties of it. Thus, first you can specify the fraction of the server heat that's removed by the liquid cooling, which we'll leave at 50%. And then you have the tube properties, one between the CDU and each row, and then that tube at each row splits then to individual tubes to all the servers. So that's what we have here with these lengths and diameters. We'll leave everything here to be default. In the data center details window, we can then edit the first row. Again, we're going to add our direct liquid heat exchange system here. And again, cycling through, we get to junctions. We'll add in our 2 junctions. Again, we'll edit our loops. So we'll edit our chilled water loop properties. We'll delete the 2 existing branches. We'll add then in our first branch, which goes from the chiller to junction J1, again with our pump F4. The second branch goes from J1 to the CRA. The third one from J1 to our liquid heat exchanger. So our supply loops are provided. The fourth is from the CRA to J2. And finally we get to the fifth one, which is from which is from liquid heat exchanger to J2. Another subtle difference between the liquid heat exchange system and the hybrid air liquid heat exchange system is you notice here there's no dash between the LHX and the 1. The reason why is because unlike the rear door heat exchange system, where we only specify the type of rear door heat exchanger, and you can then have individual placed rear door heat exchangers in each row, here the liquid heat exchange system applies for all the rows that you want to connect to it. So this LHX that we define here is similar to a CRA or a cooling tower in the sense that you define the actual piece of equipment, not the type of equipment. And since this is downstream of the LHX, we have to provide our CDU pump. So we have all but one branch left. That last branch is from J2, leading to the chiller. So if we click on Next, to Next again, we get to our input check, which gives a warning because this loop now, this chilled water loop, contains multiple fans that may conflict. But as I'll show you here, they don't. Everything is fine. And again, we have a similar layout. Here the LHX replaces the rear door heat exchanger, and we now have a pump between the LHX and that second junction. So we'll run this. And again, we have a steady state simulation output window. You can see here that the liquid heat exchanger does provide some significant heat transfer. But again, the chiller provides the vast majority of the exergy destruction. Going into our distrib folder, again we can open up our new outp file, compare that with the traditional file. So again here, we have an increase then again in the POE and our WE. But here we have a significant reduction in our CRA exergy destruction when you compare it with the traditional file. Also, you can see that we have the LHX that provides then an additional 15.6 watts of exergy destruction. But surprisingly, even though you have a higher POE, you actually have a lower total overall exergy destruction here between the direct liquid system and the traditional system. Finally, if you go to the bottom of outp, you notice that there is no information regarding the design of the direct liquid heat exchange system. The reason why there's no design parameters for liquid heat exchange system is because they're provided elsewhere. First, you've already specified the heat removal from the chips, and as far as exergy destruction goes, you've already specified in the server block what the thermal resistance is between the servers and the fluid that cools them down. However, future versions of the liquid heat exchange system may provide some equipment parameters that you could use for the design calculation.